Phenol is uniquely reactive toward electrophiles because the hydroxyl group donates electron density into the benzene ring. Today, we will explore two fundamental name reactions that introduce functional groups specifically at the ortho position, the Reimer-Tiemann and Kolbe-Schmidt reactions. Both reactions we are studying are highly selective for the ortho position. This selectivity is driven by the formation of specific intermediates and the presence of metal cations that coordinate with the oxygen atom, guiding the incoming electrophile. The Reimer-Tiemann reaction transforms phenol into salicylaldehyde. It involves treating phenol with chloroform in the presence of a strong base like potassium hydroxide, resulting in the introduction of an aldehyde group. The reaction begins with the base deprotonating chloroform to generate a highly reactive, neutral species called dichlorocarbene. This electron-deficient carbene acts as the electrophile that attacks the electron-rich phenoxide ring. The resulting dichloromethyl group undergoes hydrolysis in the basic medium. Two chlorine atoms are replaced by hydroxyl groups on the same carbon, which then loses water to form the final aldehyde functional group. In a practical setting, heating phenol with chloroform and sodium hydroxide at 60 degrees Celsius yields salicylaldehyde. This compound is a vital precursor in the synthesis of perfumes and various pharmaceutical agents. Next, we have the Kolbe-Schmidt reaction. This process involves the carboxylation of sodium phenoxide using carbon dioxide under pressure, ultimately producing salicylic acid, a key ingredient in skincare and aspirin. A critical detail is the use of sodium phenoxide. The sodium cation coordinates with both the oxygen of the phenoxide and the oxygen of carbon dioxide. This alignment directs the CO2 specifically to the ortho position. Carbon dioxide is a weak electrophile, but the highly nucleophilic phenoxide ring is strong enough to attack it. The ortho carbon bonds to the central carbon of CO2, forming a carboxylate group attached to the ring. The immediate product is sodium salicylate. To obtain the final organic acid, we perform an acidic workup. Adding dilute hydrochloric acid protonates the carboxylate group to yield pure salicylic acid. The reaction requires specific conditions, a temperature of about 125 degrees Celsius and high pressure, typically 4 to 7 atmospheres, to force the gaseous carbon dioxide into the reaction. As a worked example, consider the synthesis of aspirin. We first produce salicylic acid via the Kolbe-Schmidt reaction, then react it with acetic anhydride to create acetylsalicylic acid, illustrating the industrial importance of these phenol reactions. Let's compare. Reimer-Tiemann uses chloroform to add an aldehyde group, while Kolbe-Schmidt uses carbon dioxide to add a carboxylic acid group. Both utilize the high reactivity of the phenoxide ion and favor ortho substitution. In summary, remember that the phenoxide ion is the reactive species in both cases. Reimer-Tiemann relies on the dichlorocarbene intermediate, while Kolbe-Schmidt relies on high-pressure CO2 and sodium cation coordination. Test your understanding. Why do we use sodium phenoxide instead of neutral phenol? The answer is that the phenoxide ion is much more nucleophilic, which is necessary to react with the weak CO2 electrophile. You have now mastered the Reimer-Tiemann and Kolbe-Schmidt reactions. Understanding these mechanisms allows you to predict how phenol can be transformed into complex, useful molecules. This lesson was generated by Vision Solve AI.